tau is d by dt times dt by tau, which is 1 over omega. So d squared theta by d tau squared, which I'm going to call theta double prime, is from this is 1 over omega squared times theta double dot. So I'll get theta double dot from here and multiply it by 1 over omega squared. So I have omega naught squared over omega squared. This is what? This is delta squared epsilon squared plus delta squared epsilon squared. Multiplying here, I will have epsilon cosine omega t sine theta. So now we have epsilon here, epsilon there. Epsilon is in front of everything. That's great for the equation of motion, for your meat. Any question about that? Any questions so far? If you have a question, please stop me. So it remains to define your state space, which usually is trivial, but for this particular thing, it's a very simple system. Actually, it's not. X1 is typically theta, and what is X2? Well, usually you take a theta dot. Here in a different time scale, we would take it the theta prime, typically, right? So if you do that, what we get? We have d by d tau, x1, x2 is, remember x1 is theta, and this guy is theta prime. So the first equation is d by d tau for theta. This is theta prime. By definition, by your definition, this is x2. So I have x2. The second equation is theta double prime. So I'll get this as is here, which is epsilon times something. As you can see, there is epsilon in the second equation, but we couldn't manage to get epsilon in the first equation. Here there is no epsilon. Well, let's do it the other way around. Let's create epsilon over there. So I'll define my x2 to be 1 over epsilon theta prime. So that now when I do d by d tau, x1, x2, this is equal. Remember, this is theta, and this is 1 over epsilon theta prime. So first equation, d by d tau theta, this is theta prime. From here, theta prime is epsilon x2. So I created epsilon intentionally, that's fine. But now the second equation is for x2 prime. x2 prime is 1 over epsilon theta double prime. So now, if I get the theta double prime and divide it by epsilon, the epsilon will disappear. So I will have here this guy without epsilon. I'll have delta squared epsilon. I'll have delta squared epsilon, but the other term doesn't have any epsilon there. So epsilon is not in front of everything. So there is an issue. It's not clear how to define my state space, right? So last time I gave you like a magic representation. So let's define x2. You see this term? I want to get rid of this term. So last time I gave you this definition for x2 is theta prime minus sine tau sine theta. So this will make the first equation okay, because now if I define x1 to be theta all the way, so x1 prime, which is theta prime, is from this equation epsilon times a bunch of things. So that's good. So the first equation is taken care of, but the second equation, let's see. So the second equation, x2 double prime is, x2 1 prime. From here is 1 over epsilon theta double prime minus cosine tau, or differentiating with respect to tau, sine theta minus sine tau cosine theta theta prime. Here is theta prime, and theta double prime was what? This is theta double prime, right? No. This is theta double prime. So what is that? We have actually epsilon outside, delta squared epsilon, cosine omega t, which is tau, and sine theta. So the epsilon goes away, and this term that we didn't like, cosine tau sine theta, this guy, now it cancels out. So we made this transformation to do this thing. So we can just continue. X2 prime is delta squared epsilon sine theta. I'll tell you how to do this. Is like, I mean, of course we cannot continue like this. So I'll tell you how to, what is a constructive way to formulate these kind of things. But I'm just demonstrating here on the need of this kind of thing from the beginning. So we have this term now, and I have minus sine tau cosine theta theta prime, which is epsilon theta prime coming from here, x2 sine tau sine. So my state space model is ready now. D by d tau, x1, x2 equals, x1 here is the first equation. So this is epsilon, x2 plus sine tau sine theta. The second equation is here again, there is epsilon that I can take outside. Whenever I have theta now, I will just write it as x1, right? So this is x1 minus sine tau cosine x1 times x2 minus sine squared tau cosine x1 sine x1. This is indeed epsilon f of t and x. Everything inside is the same scale, and I have epsilon outside. I can apply averaging. Just average this guy. What do we get? So the first thing is epsilon x2 plus 0. The sign goes away. You average sine over its cycle goes away. The second is delta squared sine x1. This is a constant term, doesn't have any time. Minus the second term is 0, sine goes away. The third term is sine squared is half, the average of sine squared, cosine x1, sine x1. And you can just linearize now, right? The sine around the origin, the sine is x1, the cosine is 1. So this is 0 and 1. This is delta squared minus half, coefficient of x1. And I don't have any x2 here. If I included damping from the beginning, then this would have some damping coefficient. Negative mu. Okay? So this is your average dynamics linearized. I can check the stability from here. It's a controllable canonical form 0, 1. So these guys are the coefficients of the characteristic equations in negative. So they must be all negative, right? These coefficients must be negative. So if there is a damping, this would have been negative already. And this one remains to be the stiffness, needs to be negative. So delta squared minus half should be less than 0 for stability. So delta squared is less than half. And what is delta squared? This was like omega naught squared over omega squared epsilon squared. So omega squared, z squared over l squared is larger than 2 omega naught squared, which is g over l. Your stability criterion, okay? So we could derive a stability criterion. How much my amplitude should be, how much my frequency, in order to stabilize. You've got to choose your compromise. We couldn't do that with Fouquet. Fouquet is very powerful indeed, but we couldn't do that with Fouquet analytically, like in one page like here. You have to do many, many simulations for combination of omega and omega naught to get this stability criteria. Any questions so far? Any question? What is the main issue here? What is the main issue? The canonical form. So this guy is the issue, right? So this magic formula, I just gave it to you. We don't work like that in engineering, right? Mathematics. We have to derive things. So how to obtain a similar thing, or to get around it. So how to make it systematic? Well, this has to do with what was the main issue indeed. Let's see the main system. Our system was theta theta dot without any, any play around. Just in the time scale, theta and theta dot. This was theta dot, and this was the second equation, which was what, like omega naught squared sine theta, plus the second term was something like what remembers? Yeah, here. So omega naught squared over delta squared epsilon. Omega naught squared over delta squared over epsilon, so I have 1 over epsilon outside, cosine omega t sine theta. So in an abstract form, this is just x dot equals f of x time invariant, and here is my time variation g of t and x, but it's scaled with 1 over epsilon. Yes?
Isn't this time scale?
This is the time. It's not that.
Yeah, but epsilon appears by time scale. Like
No.
we obtain epsilon by time.
Before the time. Epsilon appears before the time. Epsilon appears because of here. This is my scaling.
Oh, yeah.
So this is the equation that I got. This one. So this is a star down. Okay, so this is the